Look up at the night sky, and you see a quiet, still canvas of stars. But our solar neighborhood actually began 4.5 billion years ago inside a violent supernova. This explosion occurs when a dying star collapses in on itself. That blast sent a shockwave through a cloud of gas and dust, triggering a gravitational collapse that ignited our star. This diagram shows the true distribution of matter in our neighborhood. The sun dictates everything, hoarding 99.8% of the entire system's mass. Every single second, it crushes 600 million tons of hydrogen into helium, generating a core temperature of 15 million degrees Celsius. That leaves a microscopic fraction, just 0.2% of the original cosmic dust cloud, to build everything else. If this central star exerts such overwhelming gravitational and thermal force, how did that tiny remainder of debris organize itself into 8 completely distinct worlds? The answer lies in distance. Our planetary architecture is strictly dictated by a massive thermal and gravitational gradient radiating outward from this single star. Where debris settled along that temperature scale determined exactly what materials it could hold onto and what kind of planet it would become. Close to the sun, the intense heat vaporized light gases and water. Only materials with high melting points, heavy rock and metal, could survive the solar furnace to clump together and form planets. Mercury sits closest, its atmosphere entirely stripped away by solar radiation, leaving a barren rock that reaches 400 degrees Celsius during the day. Just beyond it, Venus held onto a dense layer of carbon dioxide, triggering a runaway greenhouse effect. A runaway greenhouse effect occurs when a planet's atmosphere traps extreme amounts of heat, pushing Venus to a surface temperature of 465 degrees, hot enough to melt lead. Strangely, Venus also rotates backward compared to most other planets, with the sun rising in the west and setting in the east. Earth managed to hold on to liquid water across 70% of its surface simply because it orbits precisely where temperatures allow it. Our planet is uniquely stabilized by a massive moon, which prevents Earth from wobbling on its axis and keeps the climate steady enough to support biology. Mars, the final rocky world, cooled too quickly. Its internal volcanoes died out, its magnetic field failed, and the solar wind stripped away its atmosphere, leaving behind a freezing desert covered in iron rust. Early landers transmitted the raw forensic data of this barren reality, confirming an arid, rocky landscape where water now only exists as frozen ice caps. Curious. Today, autonomous mechanical rovers navigate these cracked, dry plains, collecting geological measurements to understand exactly how a planet loses its atmosphere and to scout potential landing sites for future human outposts. These 4 inner worlds share a common fate. They are dense, exposed survivors, composed of the only heavy materials capable of withstanding the sun's immediate, overwhelming heat. Past Mars, the rocky material thins out into the asteroid belt. This region contains billions of rocks and metal fragments that lacked the combined mass and were continually disrupted by competing gravities to form a cohesive planet. It is essentially a graveyard of raw planetary materials. This chart illustrates the critical threshold known as the frost line. The frost line is the specific distance from a star where temperatures drop low enough for volatile compounds like water, ammonia, and methane to freeze into solid ice. Beyond this line, gravity takes over as the dominant shaping force. Jupiter formed first, acting as a massive gravitational vacuum that pulled in huge quantities of hydrogen and helium to become the system's largest gas giant. Saturn followed, gathering so much gas that its overall density is actually lower than water, meaning if you could find a pool large enough, Saturn would float. Saturn's massive ring system of ice and rock was deeply confusing to early observers. When Galileo viewed it through a primitive telescope, the low-density icy rings appeared so strange he thought the planet had actual handles attached. While these gas giants lack solid surfaces, their gravity holds dozens of moons that act as unexpected havens. Jupiter's Europa hides a global ocean beneath its icy crust, and Saturn's Titan features flowing rivers and lakes of liquid methane. Out here, the sun's heat is an afterthought. These volatile behemoths were sculpted almost entirely by gravity, collecting the immense volume of light materials that the inner solar system couldn't hold onto. Further out sit the ice giants, locked in a deep freeze. Uranus rotates entirely on its side, an anomaly likely caused by a massive ancient collision that allows its core heat to leak away into space, dropping its temperature to -224°C. Neptune is nearly as cold, yet it whips up supersonic winds reaching 2,100 kilometers per hour. It is also the first planet discovered not by scanning the sky with a telescope, but by mathematically calculating how an unseen gravity was pulling on the orbit of Uranus. To understand this dark environment, humanity constructed robotic emissaries like Voyager 2. Equipped with specialized scientific instruments and a golden record of Earth's sounds, it survived the extreme cold to closely study all 4 giant outer planets. Past Neptune, the system dissolves into the Kuiper Belt. This vast ring of icy debris and dwarf planets, including Pluto, orbits in a perpetual twilight at temperatures hovering around -225°C. The Kuiper Belt marks a physical limit. It is the freezing boundary where the sun's gravitational grip finally weakens and the scattered remnants of the original gas cloud fade into the void of interstellar space. Looking at this arrangement from Mercury's scorched rocks out to Pluto's ice, the solar system is a precisely structured thermodynamic gradient. But it is not a permanent fixture. In about 5 billion years, the sun will burn through its nuclear fuel. It will expand into a red giant. A red giant is a dying star in the late stages of stellar evolution that swells massively as its core contracts and its outer layers cool. As it grows, it will physically engulf and incinerate the inner planets, including Earth. Eventually, the sun will shed its outer layers and shrink into a white dwarf. A white dwarf is the dense, fading core left behind after a star exhausts its nuclear fuel. Billions of years after that, it will cool completely into a theoretical black dwarf, emitting no light or heat, and permanently shutting down the mechanics of the system. Our solar system is a temporary, chaotic engine winding out its clock. We happen to exist in the exact window of time and at the exact physical distance from the core, where liquid water flows and biology is possible.